All of them are open. Right?
Almost always.
Vladimir talking about disks, planets, and pencils. Please.
Thanks, man. I'll be talking later then on what I have been doing with the pencil code. It's about disks, planets, and then how we use pencil for doing that. So first about some of the simple physics of the problem. Planets form on disks around the star, right? And we have a cloud, and then there will be some denser clouds in which the stars will be formed, and then as you have angular momentum being conserved, there will be a disk forming around the two as the matter collapses to form this star, and the planets then will be formed on this circumstellar disk. Problem is that protoplanetary disks, they are not exactly easy to model because they are, say, turbulent, magnetized, dusty, radiating, always in non-LT, self-gravitating, and then also thin. So there is just too much complicated physics there. So then the approach that we take is simple. We just do one thing at a time, right? So then we see here that the most recent computational advances done. Everyone solves just one simple part of the whole problem, always leaving something not done. And then we have like several different people working on a different part of the problem using a different code. So then how do we know if we can trust what is being found? So then someone came up with a very simple idea. Let's all run the same problem, and then we see if we get the same thing out of it. So then the problem which was set, it's a simple one. Let's make a 2D disk, place a planet at a radial distance which will not change, and then try the planet having two different reduced masses, which is 10 to the minus 3, which is roughly Jupiter's reduced mass, and then 10 to the minus 4, which is Neptune mass. And then we smooth the planet potential with this equation here, where epsilon is the smoothing length, which is 1/5 of the Hush load. And we also need radially varying sound speed. So then sound speed changes with the radial distance on a way that we have the Keplerian flow having a Mach number 20 everywhere. So there are codes which are Cartesian and some other codes which are polar. That's the resolution which we use. Those numbers here, they were chosen to have a cell size which is the same size at the planet's location. And then the radial domain runs for 0.4 to 2.5 times the distance where the planet is. So then visually, that's the initial condition here. We have a global disk here, right? Which in pencil, it's in a Cartesian sheet. So then here, the parts here which are within these two lines, they are the evolving parts. Everything which is out will be turbulent. This is the initial density, the angular velocity profile and the sound speed corresponding to this angular velocity profile.
It's like a Cartesian grid or
That's a Cartesian grid.
And how can you compute the radial profile in this case?
What do you mean by that?
How can you plot some kind of radial profile? It's the radius here?
Yes. Yeah. Here, that's the radial distance.
Okay, how do you do that?
Well, it's a post-processing here, right? So then I just take the var files, and then I read everything, and then I change the cells from XY to R5 afterwards. Does it make sense to you? No? Okay, and the boundary condition is simple. Polar grids, they use a reflective boundary, which is just silly. I don't know why they do that. They just use that just so they can assure that they don't lose mass. But then what it means is that if you have a wave coming, when you reach the outer boundary, it will then bounce back, which is totally non-physical. But they just find that it's not a major thing, and they can go along with it. I don't use that. What I use here are the buffer zones. So then I have a buffer zone from 0.4 to 0.5, and another one from 2.1 and to 2.5, where I will damp motions. So then the wave is really killed before they can reach the real boundary, and then they are killed with this expression here, which I use for all of the variables, for density, for the velocity components, and I also use it now for the magnetic vector in the turbulent run.
But if you damp the velocity artificially, that doesn't make it more physical necessarily, does it?
I'm not sure I understand your question.
I mean, it's perhaps not more physical to damp the velocity artificially than have a reflecting verse on the boundary.
Yeah, it's an open boundary.
Effectively, perhaps, but there's no such thing as a damping mechanism.
It's no more realistic, that's true, but
Yeah.
the effects may be slightly less
So then we use an artificial viscosity of 1 to the minus 5. Everyone agrees with that? And then we simulate it over 100 periods. So then here we have the initial condition, and I have a little movie here of how it evolves. So then here we follow the planet for 10 orbits. So you see the wake forming as trailing waves and forward waves. And then here we change to a co-rotational frame, where you see that we have a stationary wake, and then we see the density gap here just getting deeper as the time goes on. There is some numerical thing happening here in the inner boundary, as you see. I will talk more about that later on. So, do you want to see the movie again, or was it cool to listen? In the inner disk, you see some numerical things happening, but it shows more in the co-rotational frame. as soon as it gets to 10 orbits, you will see, okay? So we can move them. And then here you see something moving which shouldn't be doing.
Are we looking at this as calculated in the code moving frame, or just looking at it in the code?
Looking at it.
Okay, so it's calculated movement.
Yeah. So it is ran on an inertial frame, but here plotted on a rotational one.
So actually,
That's
the
how
thing
we
that's
had-
moving there is the stationary thing.
Yeah.
So you're seeing the mesh move.
Yeah, exactly.
Okay, that's it.
Yeah. And here, that's the density evolving in time. From time here, it's been shown in orbits. So then here, from 2 orbits, 5, 10, 20, 50 orbits, and 100 orbits. So then we see the density getting deeper, and then as we conserve mass, the mass which was here goes to the two Wlad1 resonances. So how do the different codes work now? We had all of those codes here. Some of them work on a not-linear method. Shock capturing methods, we have those. Particles, SPH codes. There were 2 of them, and then we had this other classification which was open just for pencil, because no one knew how to classify it. So then we just opened that another one there, high order finite difference method, which there is just me there.
So that was visual thing to distinguish between open and shock capture? Yes.
Yeah.
Yes. But both are
That's a standard thing.
No. Open don't capture. Artificial intelligence. That's what it's put well, because it's not the numeric scheme of shock capture. Shock capturing method usually refers to something based
the wave problem.
Yeah, like
It really
captures
captures something.
exactly. Yeah. Why doesn't open do that?
Upwind is just finite differences.
Oh, it's
Pretty much just with the derivative done in a kind of fancy way that isn't so badly affected by.
You still need the artificial shock capture on top of the open?
It depends. I mean, upwind methods can include TBD, right?
Huh? Thinking about something? Because you're looking like with a business and...
No, I mean, I'm just saying, or thinking that upwind is not the whole expression. I mean, you have also, of course, the TBD, yeah, exactly. I mean, there's a German term for that. What's it called? I mean, how you write the flux.
Yeah, right, the flux.
Yes. So upwind is not. I mean, otherwise, a high order scheme can equally be upwind, and it would still not be anything like what you mean by upwind. I think.
Are we doing this actually for upwind derivatives?
What?
Are we doing this?
Yeah, we do actually. We can do upwinds. Are you actually doing this? Are you doing this?
What?
I mean, we have a switch of using upwind derivatives for the density and
Yes, I am using that for density only. But then Wlad1 said that it's a detail which doesn't have much to do with the upwinding classification of a code.
No, upwind usually means TBD, and hence will also mean at the most second order, right?
Mm-hmm.
But sometimes you hear intensive connections, things like we use a shock and explicit viscosity to shock capture shock. Like that. I just find confusing.
It is confusing.
I mean, which book do you go and see these instances, or is it just kind of the numerical Bible again, the one that actually owns for a numerical Bible?
You have to go look at the individual papers. Well, I think all of those codes are listed there in the upwind box are TBD schemes. If you mathematically sort of push everything through operators and things in what a TBD scheme is, you can make it look like a finite difference scheme, and you get what looks like a diffusion term. But you never actually evaluate it because it was in the thing, right? And that's what we have in the print terms, that contribution.
Okay. So we have this density max here. That's the same thing which I showed on a Cartesian sheet, but in radial distance and angle phi, right? So these are the flows which they get with particle, radix, flash.
That's shearing sheet actually? Yes.
Yes.
No?
That's a 2D, right? No. It's a global disk, but in 2D.
Because it looks almost as if the lines could be periodic.
They are, because they are. It's all of these here. They are cylindrical codes, right? So then they.
But
huh?
if phi equals -1 and +1 does not mean that -1 is the same position as +1 or what?
Yes.
It's divided by pi.
Yeah, like
Okay. Right. Okay.
Pi here
Yeah, I see.
over pi.
So you just wrapped this whole thing open into a single energy.
So you have the same code here in Genesis, Global, Jupiter, and Nirvana. There are two more Nirvana, which are the same code ran by 3 different people. These are the one of the particle codes, RH2D.
Hard to believe that's the same problem. That's the H one.
And then here, pencil, flash, RH2D again RH2D, or is it wrong? I think that I put the wrong here. Should be trying. And then here the other particle code. Yeah, you see that. Yeah, that's actually one of the main things that we found here in this project. That if you want to model that problem, you shouldn't use the particle methods because you get something like that.
So the lower right is what?
The lower right here,
Yeah.
RH2D. It's Nirvana-like code done by really Pi. And here, pencil.
So is the problem with these page codes that they're too diffusing, or I mean, they cannot maintain any sharp structure?
I think that the main thing is that in this problem we have a lot of time low density regions happening, right? And in a particle method, I mean, a low density thing means that you don't have much particle there, so they just can't resolve it so well. Right? So then here we have the radial averages of the density profiles of the different codes. You see that they all agree quite well, with some exceptions here, which are the 2 particle codes which you see here and here. This is the residual which we get after taking the average of all codes. The interesting thing here for us is what pencil does. What we see here, pencil is this purple line here. We see that we have a shallower gap here, and a linear disk which has less mass than the other ones. So these are the 2 main differences from pencil to the other codes. Here then, that's an azimuthal slice which we take at the radial position where the planet lies. So then we see here the density peak due to the forming planet, and then the density profile in the depleted gap. We see here pencil like just a bit upper than the other codes due to the fact that we have a shower cap. And then this mass, how it evolves. Pencil is there. I don't know if you can see it, but it's here. It's this line here. So it's in the middle of the other codes. Fine. Then, but then every single code does quite similar. Apart from the Flash AP, which is the Cartesian version of the pencil code. Of the Flash code, and that's the only other Cartesian code there. So then, before I sent my run, he was blaming the Cartesian grid for this mass loss, which I show here that it doesn't happen on pencil. So then I think that he has to find another excuse for this thing.
Amazing, right? That's quite amazing. Such a huge mass loss.
Yeah, exactly.
Can you show him what the Flash AP gave for results in the audio?
No, it doesn't look much fun actually. I mean, if you go back there, Flash AP is this one here.
Yeah, it's wiggly.
Yeah. And you see that it's wiggly thing. I think that it happens because he doesn't use diffusivity. Yeah, I tested it there with the pencil code, like several different diffusion things, hyper diffusions, shocks, and then saw like how it behaves there. I will show it later on.
It looks like it just piles mass up the planet and never stops.
Yeah.
So you just end up chopping the top off, right?
He probably only relies on the dissipation he can get from the Merkel scheme, whereas you have been able to defend the play around and see what kind of dissipation you have taken on.
Exactly. So let's keep on going here. So this is the disk mass, the evolution. The only thing here is that in the mass accretion rate plots, we see that pencil has a different slope than the other codes. Here is pencil, we have this, and it goes a bit upper, and then you can see it rising. So then, which means that we lose less mass than the other codes do. Angular momentum here, we see once again that we have a different slope than the other codes, possibly due to the less effective mass loss.
So what was that last plot?
Angular momentum. It's density times.
Of the planet?
Sorry?
Of the planet?
No. Of the whole disk. No.
That's the line in the middle then, yeah? Where is it? It's the line in the middle, right?
Which one? That's it?
Yeah?
That's it.
Right. And why do you stop?
That's the purple line, huh?
Why do you stop at 200?
I stopped at 100 actually because they just asked to send up to 100 orbits. And but then there were some people who ran 200 orbits, and then some freaky people who ran 500.
Yes. No,
Yes, one of the flash groups had 3 flash, right?
Yeah.
but then you should also run for longer, right?
Sorry.
Then everybody should run for longer or something.
But
But they should.
They just want to show up. Yeah.
It's like all of a sudden some of the people didn't do their job correctly. Were lazy, had to catch a train or something.
Yeah, but that's what the manager at Flash would have wanted, of course.
That could be.
I'm sure the government expanded.
So here, torques then. These are the torques from this onto the planet, and here those are the Wlad resonance torques. And then here, what the codes get. We see here pencil. It's this line here that you can see, which is right well between the other codes. That's a fine profile, so we see that we are doing well here. And the total torques, we see that in all codes there is a dispersion of a factor 2. Here goes from 0.2 to 0.4, and then here the same thing happens here from 0.3 to 0.6. These are the torques from the inner disk and here from the outer disk. You see that pencil has the biggest torques of all codes. We tried to see why it happens, but we have no explanation for it. But we don't think that. We think that it's a problem on the normalization that everyone did for the torques. So it's a weird thing that we have a factor 2.
I mean, if you show the value profile, you show the inner disk and then so on. So is that also the fault of the control?
If it was like that, you would affect the outer disk too, right? Yeah, like we see that it happens on both, here in the inner disk and here in the outer disk too. So it was just the inner disk which had the depletion, right? So then I could understand if we had different torques in the inner disk but not in the outer disk. But it's not what is happening.
So what code is Fargo? Fargo is the one which these
Fargo
figures.
is the blue one here.
Yes. So what is why are these figures in the?
Sorry?
Why are the figures?
Wiggles?
The figures? Yeah.
I actually see wiggles too, but this is a moving average, right? So then probably he outputted more often than the rest of us did. Yeah.
Why? Because then you should actually average them away, we would think.
Yeah.
You should not see the figures.
Yeah. No. One should not see them.
But the core, of course, could always generate figures if it doesn't resolve properly.
Well, they don't mention anything about that in the paper. If it's a problem that we have wiggles there on the torque time series. But I noticed too, but they average out in the running average. I don't know what he did there to get torques like this one here. Yeah, with the wiggle thing. But you see here that you have wiggles when you have the lower torques, right? You see that there are some wiggles here, and then when we get to higher torques, the wiggles just disappear. So it might be that, but I'm just calculating here. I don't know. This is the power density of the torques. That's a messy plot. Yeah, that's a messy plot. But what you see here is that we have peaks in frequencies which are in the resonance positions with the planet. So that one here is in 1, that one here is in 0.7, and then another one there in another resonance. So it's we see here that the codes agree quite well in the position of the torque peaks in the power density factor. Here then we have vorticity. That's the vorticity profile. We have a lower one here because we have depleted inner disk, right? So then, well, like here, we have higher up because we have less density here. So then you see that we have a higher density due to this thing. And then in the gap, we also have less vorticity due to the fact that we have a shallower gap. But what is interesting here is to make a comparison of the two Cartesian codes on the vorticity profile. We have pencil and then flash AP, which is the other Cartesian one. That's a Nirvana run in a C Linux code, so then we see how it should look like. On pencil, okay, we have something here, right? But it's not extreme as it shows on the flash code, right? And then you see it here. When I saw it here the first time, I knew quite well why that can happen. That's what happens if you use too few resolution, or if you don't use diffusion. So that one here, that's a run, like with the same hyper viscosity and the same hyper diffusion. Here, if you run 320 square, and then here, if you run 256 square, you see that the two of them, they are in the same time. So, these are the modes which you saw there in the flash code. It's that wiggle here, and here, which appear in the locations where the flow diverges most from the Cartesian read, right? Where the flow geometry diverges more. You can see it here, in the flash code. You have here 45, 45, 45, 45 degrees. See that?
Yeah.
Mm-hmm. Look.
Yes, exactly. Right, good.
So then here I measured the influence that the hyperdiffusion coefficient has. Is here, that one, it's a comparison run which I ran with a 640 square resolution. And then the other ones, they are in the 320, so then they are lower resolution. And then here, with different hyper diffusion coefficients. So then here I see the one which I ran with 5 times 10 to the minus 11. And then I go all the way down until the green line where you see run which has hyper diffusion 10 to the minus 14. What you see here is that it clearly makes an influence in the gap, right? And then in the inner disk too, we have different things if we run with different hyper diffusions. Due to that thing there, that we don't hold the inner disk quite well if we don't choose the right hyper diffusion thing. What?
It's interesting that it's not monotonic on the inner gap.
No?
That's weird.
Yeah. Sure. But here then, there's one thing that when I saw the first time also it struck me is that these are runs all of them with a higher diffusion, 10 to the minus 11. But here you see what happens if I don't use shock diffusion. That's the black one here. And here, with a shock diffusion coefficient of 1, of 10 to the minus 1, and here 10 to the minus 2. If you guys explain why this thing happens, I would be extremely glad.
Adding more food? Adding more food and taste better?
I'm sorry?
Adding more nutrition and taste better?
Yeah, but it's supposed to happen only where I have a shock, right? But then here I see it happens through the whole disk.
Well, but you plug, I mean, do you know what's the RMS like through the disk? I can't.
RMS. What do you mean by that?
So how does the velocity profile look as you go out into the disk?
It's K-Player profile, but with Mach number 20.
Is it it's fixed, is it?
It's fixed.
And what happens with the shock coefficient? You have your shock and shock diffusion.
Yeah.
And you have the shock diffusion.
Yes.
You mean shock resistivity? When you say diffusion, do you mean thermal or?
No. Density. Yeah.
That's mass or density
Yeah.
diffusion?
Mass.
Oh, right, sorry.
Yes.
So,
Aha.
I mean, this is what happens, right? When you, I mean, I guess, okay, so your question is why does it happen even when there are no shocks? Or maybe there are shocks, and I mean, it depends on the whether of no shock. So how many grid points?
320 on X. And yeah.
So you want to look at that gradient, it goes from like the inner peak to the first value. And then you might consider whether that is resolved or not. Because I guess, I mean, the shock coefficient should really tell you over how many grid points your shock.
That's pretty much what it works out to.
Yeah.
Basically, it's a rule of thumb. It's about approximately how many points. There's a factor multiplying, of course.
So if you have a shock coefficient of 1, you might remember it's not dimensional, then it should spread out all gradients over the one grid cycle.
Exactly. Well, like 1 could correspond to 5 or something.
Yeah, but here it says that when you have a shock of 1, it's spreading that gradient over like 100 grid cells or something. So maybe it's just too much shock. I mean, you need one or could you do it also 10 with 10 minus 2? I mean, no shock actually works. Okay? Because no shock works. It works without shock. Without shock diffusion.
Yeah, it does.
So the question is why a limited shock round of 1 gives you something that spreads out over 100 grid cells.
Okay.
And this should be non-dimensional.
Didn't it change? Didn't you non-dimensionalize it at any point?
No.
Shock's always been that much. It's always had a dx.
Okay.
It should actually be a dx max square, I think.
It is.
Or something that's dx min.
Or should it be dx max? Not be dx min, it's something like that. One over dx max.
Okay, let's then keep on going here. Okay, time then. As you guys were concerned here, we have the time here for the different codes. At the time that one processor would take to run 100 orbits. And then we see here that pencil shows up being with 36 hours, where the other ones usually show much less time. So it was a thing that you guys found with issue, right?
Yeah. But does that hold in the number of processors and like a CPU hour, or is it?
This is in CPU hours. You see here.
Single processor.
Execution time on a single processor in hours per 100 orbits. So I was thinking about it, and I could point some things that could be the reason for that. The first thing which I mentioned there in the lunchtime is that we spend 30% of the time calculating frozen zones. And as you see here, I mean, I am interested only in what happens here, right? But then I had to also solve here and here and here and here too, which then take 30% of the whole computing time. To a region which will not be
Did you try
good.
to profile the code and look where most of it is spent?
No. I wouldn't do that.
Yeah.
But that's, I think the trivial answer is that it's crossed the route at all.
Okay,
that
would be a good guess.
No, yes, I've run it through the profile many times. And
I mean, like, maybe it's something specific to this problem.
I think
No.
it might be.
oh yeah, but you still have
But
responsibility. Yeah.
that's how it's.
Yeah, that was the other thing, that we also have shocks. So then some time is being spent calculating shocks. I don't know how much time, as you asked. I mean, I didn't do that calculation.
On the shop.
The shock calculation.
Yes. All in all.
50% in speed. That's impressive.
Yeah, this is why I've been
It
using
might
this.
only be if
This is why I've been using this different one.
it's definitely true to
Which one?
And
This Gauss interval thing.
Okay.
And another thing also,
Okay, let's do anything else. Divergent smooth max. 30%? I mean, it's taking a divergence, so what? I mean, it's not immediately as elaborate as
It's
taking
first
all
order.
cross derivatives.
It's the first order divergence.
And it's first order.
Yeah, it's good.
pretty good at thing. Another thing is that my time step is actually smaller than needed, because I have the highest speed in the frozen inner part. As you guys see here, that's the angular velocity profile which I use, and then here that's the frozen zone. I have highest speed happening where the flow will be actually frozen. So then the other codes they use for the
You said the time step. The time step calculation is going to include the inner bit, you mean?
yeah.
Does it really?
Exactly. That's it. I mean, the time step of theirs will be constrained by the speed which you have here, and in my case goes to some speed which we have in the frozen zone. So then, yeah, like
Have you tried to cut out the effective time step calculation that the boundary? Or just ignore what it says will be done?
What is that?
you mean like to use fix the time step?
Just don't take anything that happens in the inner boundary into account for the time step calculation.
No, I didn't do that.
Or maybe
Can we do that in the
I mean, are you still talking about timings?
Yeah.
I mean, for example, have you checked the length of your time step in connection with the length of other people's time steps?
No, I didn't check that.
So, for example, suppose you have something crazy with your Courant condition, then your time step is all of a sudden 10 times shorter. then of course you require 10 times more time, right?
Because this actually is precisely what I think the reason for the 30% slowdown is in the shock viscosity. Is that it can put X in the viscosity, which seriously limits the time step.
And which is not really,
very good.
and also not required, one would think. Yes.
Okay. Good.
So you actually take
So then, conclusion. There's nothing much to say about it, apart from the fact that Hansel agrees quite well with the other book. That's right. That's the main thing that we found about that. So then, this is a project which is over now, and then we are thinking about doing some other things. As I mentioned, I am now running a turbulent disk with Anders. So that's a sample run,
Elliptic disk.
which we put a vertical field in the disk, and we see like how it evolves afterward. We see here turbulence coming out from the outer disk into the inner disk, where it reaches a saturation after some time. I didn't run further because I ran out of space.
This was
With the
2D or 3D?
Fake 3D. So
You mean the so-called cylindrical disk?
No.
Yeah. I mean, that's still a good, interesting approximation, by the way, because you get rid of certain problems, but you retain certain interesting aspects, like the global aspects, and you can potentially get large-scale magnetic fields if you get a dynamo to run. Are you trying to do that? Are you trying to do that? Turn off the vertical field and get a dynamo?
Yeah, I tried. It doesn't work.
It's not exciting to me.
No.
Maybe you need more points.
I tried there with noise on the velocity profile and then in the magnetic too.
Yes.
So then I get some turbulence for say 2 orbits, but it then dies out after some time.
Need more points.
One
So we
problem,
need external fields.
one problem that is formulated. So in the zero box, because we have this standard way of using zero net flux.
Yes. Yes.
Formulating this in the global system was a bit more complicated than it did.
Right.
And that's for B field.
Well, you just
And what cases and what should we have to do? Wasn't that trouble for formulating, even though we knew exactly what the B field should look like in the initial condition?
Yeah, we had trouble with
to
that.
formulate the A field. I mean, it was just really big. I mean, one prime example that general is a constant reset field, which is trying to formulate with the vector position instead. I mean, there are certain things that are easier to formulate with the B field than with the A field.
But a constant B field is, of course, trivial. You just add it on.
Sure. Yeah, right. But then
I'm formulating from A, basically.
It's also trivial. It's just an equation. Yes.
But then you don't have periodic boundary.
Yes.
Right? Different quantities, you have something varying in some direction and you can control the periodic boundary.
Yeah, but I mean, there's no issue. I mean, that's just how it is. If you have a vertical field, and this normal thing you would do is just add it on, of course.
And that was the main problem. I think we found some kind of nice way to zero network global distribution for the B field, but it was just immensely difficult to do anything in
Okay. Okay. Yeah. Thanks very much, Vladimir, for a very interesting talk. So.